In this video, we're going to talk a little bit more in depth about something that has come up once or twice already this year. It's called concavity. The word concave technically means hollow. So when you talk about concavity, you're talking about the side which is hollow or empty. You kind of can think of it as a cup is hollow on the inside. This is the part in here where that curve I just drew is hollow. So when we talk about concavity, what matters to us is which direction, up or down, is the graph hollow. So we could have graphs that are concave up, meaning the hollow side is facing up. Or we could have graphs that are concave down, meaning the hollow side is facing down. Notice, very importantly, that concave up and down has nothing to do with increasing or decreasing. The first function that I drew was decreasing, and then it was increasing, but the whole time it was concave up no matter what. It was concave up no matter whether it was increasing or decreasing. So please don't confuse the two. Increasing, decreasing, and concavity are not connected. So a function is not usually always concave up or always concave down. A function can switch from one to the other. Like you could have a function that starts out being concave down, but then switches to being concave up. You know, it's harder to picture this as hollow here, but if you imagine that this bend would have kept going the way it was headed, it would have bent back down like that, and that would have been concave down over here. So up until here, this graph is concave down. But then, almost magically, it just switches from here. You can see going on this way. If you can imagine it continuing like that, the graph would be concave up. And so from this point on, the graph is concave up. That spot right there, where the graph switches from being concave down to concave up, is called a point of inflection. It's a spot on a function where the concavity changes, either from concave up or to concave down. We're going to take a closer look at this concavity. We're going to connect it to other things we've learned this year. So here I'm going to sketch a graph of something that is concave down. I'm going to make it nice and widely spread out, but it's concave down this whole time. Here's a graph that is concave down. What we're going to do is look at the derivative at various points on the graph. So I'm just going to number them 1, 2, 3, 4, and 5. Don't worry about what the actual exit value is. It doesn't matter. But if we look at this point, the slope at this point is pretty steep of that point of tangent C. So if we were to find the derivative of the function, let me just label this green function as f of x. So f prime of, I'm just going to call this 1, is a pretty big number. I don't know, let's call that 3. But then what happens as x moves along, so the graph still has a tangent that's facing up. The slope of that dotted line right there is still positive, but it's a lot less steep. So maybe now f prime of 2 is, let's say, 1/2. It got less steep. At the top here, we know very well by now that at a relative min or a relative max, that tangent is going to be perfectly horizontal. So f prime of 3 is 0. Notice again, the f prime, the value of the instantaneous rate of change, has decreased again. Well, if I keep going, pick a fourth point here, notice the graph, it's not flat anymore. It's gotten a little bit steeper, but it's steeper negative. Now the tangent line has a negative slope where the instantaneous rate of change is negative. So f prime of, let's just call this 4, is now negative. I'll just call it negative 1/2. And then later on, the slope is still negative, but even steeper. So f prime of 5 has gotten even lower. Let's call it negative 3. So hopefully you can see what I'm getting at here, that when a graph is concave up, its derivative, it was 3, and then 1/2, and then 0, and then negative 1/2, and then negative 3. That derivative has continuously decreased. So the derivative is decreasing. And that is a big, big, big connection to make. A function is concave down, means its derivative is decreasing. Those two things go together. They happen at the same time. There's another way we can say really the exact same thing. If the derivative is decreasing, we've said many, many, many times this year that any function is decreasing when its rate of change is negative. That's what it means for a function to be decreasing. Its rate of change is bringing it down. Well, the rate of change of the derivative is what we call the second derivative. So a function is concave down when its derivative is decreasing, and derivative decreasing means that the derivative of the derivative is negative. So a function is also concave down when its second derivative is negative. These are two ways of saying the same thing, but it is a very important thing to be able to say. Of course, the opposite would be true for a graph to be concave up. A function is concave up when its derivative is increasing, which means a function is concave up when its second derivative is positive. And those are very important facts to memorize. One more thing we're going to do with this. Before we get to one more thing we're going to do with this. Another way of understanding the second derivative is that it measures what's called the curvature of a graph. So a graph that has high curvature means its rate of change is changing fast. This graph, this parabola, it was very steep increase, and very quickly it gets flat and becomes a very steep decrease. So the rate of change is changing very quickly. That's a high curvature. That means the second derivative is very, not big in this case, but is it's far from 0. It's a big negative number in this case. So I can say the absolute value of the second derivative is big, meaning the graph is changing quickly. On the other hand, if I had a graph whose second derivative, or the absolute value of the second derivative, is small, that means there's low curvature. That means the graph doesn't really matter if it's increasing or decreasing, but it's changing the rate of change of this graph is changing very slowly. Yes, this function is concave down, which means its rate of change is decreasing. Its second derivative is negative. So it has a positive slope here, and it's getting less. Positive slope here, it's getting smaller, 0, smaller. So the rate of change is decreasing, but slowly, which means that the second derivative is a small number. I'm making up numbers here, but let's say in this case, the second derivative was like -5, because it's making the rate of change, or f prime, change very quickly. Here, f double prime was not such a big negative number, which means it is having a slow effect on the rate of change of f. Okay, now, one last thing I'm going to show you. And this is a common thing in a calculus class. It's to make what's called a sign chart for both f and f prime. F prime and f double prime. So what we're going to do to make a sign chart is analyze whether at different moments in the graph, so for different x values, whether f prime and also f double prime is positive, 0, or negative. That's all we care about. For whatever x values we choose, I want to know is x positive, 0, or negative. So, for example, in this case, maybe we would pick, I'm going to focus on this point, x equals 0, sort of as the middle here. And then we'll look before x turns 0. So back here, when x is negative, f prime of x, by looking at this function, because this function is increasing, we can say that f prime of x is positive, which means that we can say f of x is increasing. We can also say that when x is positive, so out here, f prime of x is still increasing. Sorry, f prime of x is positive, which means f of x is still increasing. Although, so it seems like we can say, oh, this function is always increasing, which you could, but there's another point to be made here, which is that at this exact moment in time when x is 0, f prime of x is not positive, because at this point the tangent line is perfectly vertical. So f prime of x doesn't actually exist. So you can either write does not exist. If we wanted to be a little bit more specific here, we could say that it is approaching infinity, which means that f of x is vertical, or has a vertical asymptote, vertical tangent when x is 0. You'll see examples in class moving on where we actually do things with this. Right now, I just want you to get used to this idea of using a number line like this to describe one element of a function, and then use that to describe what's going on with the function. Okay, so we'll do another example. You'll see it with f double prime. So we'll do the same thing where we'll look at what f double prime is before x is 0 and after x is 0. So over here, when x is negative, so in this section in here, looking at the graph, we can see it appears to be concave up. The graph is facing, the hollow side is facing up, which means, we can write that down first if we want, that the graph is concave up. And that means that f double prime of x must be positive. On the other hand, when x is bigger than 0, we can say that f double prime of x must be negative, because we can see on the graph that f of x is concave down. If it helps, by the way, if it's easier for you, you can feel free to use pictures to show concave up and concave down. If that's something that's easier for you to understand, be my guest. Similarly with increasing, if it's easier for you, you could have used an arrow pointing up to say that the function is increasing. If you like that better, be my guest. One other point that I did not mention here in the second derivative sign chart is when x is exactly 0, the second derivative is neither positive nor negative. If the first derivative doesn't exist at that point, we know that the derivative of something that doesn't exist couldn't possibly exist. We know that you can only take the derivative of a function that's continuous. So if a function has a discontinuity, it also won't have a derivative at that spot. So the derivative of the derivative, the second derivative, also can't possibly exist at that spot. But notice how the second derivative switches from positive to negative when x is 0. F of x switches from concave up to concave down when x is 0, which means that when x is 0, there must be a point of inflection. That's all I wanted to include in this video. In class, we'll do a little bit more. We'll go in the other direction. We'll take a look at a sign chart like this and try and sketch a graph based on it, so that way we can go in both ways.